Hey, Mr. Harridan here.
Well, it's nice to meet you all. There's sodas in the fridge.
Okay, and we're going to discuss covalent bonding structures with you today here. Okay, so in covalent bonding structures, sometimes the more electronegative element is not strong enough to take another atom's electrons away. The electrons of both the atoms placed between the two are shared, which is a covalent bond. Remember, in covalent bonding here, we're talking about two non-metals. And there are two ways to share. Okay? You can share equally, which is non-polar. Or you can share unequally, which is polar. Polar. Unequal sharing. Uneven electron density, of course. Okay, we did this a little bit already. Predicting the substances, covalent bonds are always between two non-metal elements. Okay, on to page, whatever the next page is. Page 9! Okay, doing the calculation thing here. Non-polar covalents are shared equally, approximately, between 0 and 0.3. So this is equally. The electronegativity difference is less than 0.3, which we learned in the previous video. Okay. Now is a great time to memorize the diatomic elements. These elements are so electronegative, they do not like to be by themselves. There are 7: iodine, bromine, chlorine, fluorine, oxygen, nitrogen, and hydrogen. I bring clay for our new house. Okay? If you're looking at the periodic table here, this is one way I know them. I started iodine. I bring clay for our new house. Because it makes a 7 right here. 1, 2, 3, 4, 5, 6, 7. Okay? And then the 7 point's actually over there. Okay. Those are the non-polar covalents. Okay? All diatomic elements are non-polar covalent. Then we get to my favorite here. Polar! Where electrons are shared unequally. There is an electronegativity difference. Hey, did I mention that we're talking about polar covalent, right? This is when the electronegativity differences are between 0.3 and 1.7 here. What's going to eventually happen is you're going to have a partially negative and a partially positive side of these polar molecules. Okay? There is a partial positive, which has less electron density, and there is a partial negative, which has more electron density. So if we're talking about polar bonds, right, and we're trying to share 8, the one that has more of the electrons, like this one has 7, this would be the partial negative end over here, and then this would be the partial positive end over here that only has 1. Okay? And you use the electronegativities to determine that. Okay? So what you do here is you label each element with its electronegativity value. Okay? On the test, the electronegativity values will be given to you in the question. You place an arrow above the pointing element to the more electronegative element, and then you place a partial positive on the more electronegative element and a partial positive on the less electronegative element here. So for instance here, okay, I got these memorized, so I don't need to look these up. So for instance, oxygen I know is the electronegativity of 3.5. Hydrogen has an electronegativity of 2.1. 3.5 minus 2.1 is 1.4, which means this is polar! Just so you know. So I would label this element as partial negative, and I would label this element as partial positive. Okay? Now, you can also draw an arrow. You draw an arrow like this towards the more electronegative element. I usually put a plus sign at the end of this one. That shows me that there is more electron density on this side, because this has 3.5 electronegativity. This one wants electrons more than hydrogen does, and this one would have less electron density. Okay? Because it's 2.1. Okay, I guess I should say that also the electronegativity difference was 1.4 in here too, which proved that it was polar covalent. Okay. Show the direction of pull for bonds within F2 and HCl. So we have F2. Okay? So we have F bonded to F. The electronegativity of F is 4.0. The electronegativity of F is 4.0. You can look those up in the reference packet. So here, my electronegativity difference is 0, which means there is no pull, which means that this would be a non-polar covalent bond. Okay, that would be F2. Okay, now let's look at HCl. HCl would look like this. Okay, the electronegativity of CO is 3.0. The electronegativity of hydrogen is 2.1. The electronegativity difference here is 0.9. 0.9 would tell me that this is a polar covalent bond. Okay? Which means, since CO is more electronegative here, so this would be partial negative, hydrogen would be partial positive. I would draw my arrow, my dipole. I should call this a dipole because that's what it is, Mr. Harridan. These arrows are called dipoles. Points towards the chlorine, which means that the chlorine would have more electron density than the hydrogen, which would have less electron density. Okay. Yeah. Okay. Now, last question in this video here. Maybe I should find some more sound for us here. We need another sound here. Oh, here's what I hope for on our test here. Ready?
Dear Bill and Ted, good luck on the report.
Good luck on your chemistry test.
Bill S. Preston, Esquire, and Ted Theodore Logan. Oh, that was nice of us.
That was nice of you guys. I wish you guys good luck on your test. Okay. Final one here. How many polar bonds and how many non-polar bonds are in CO2CO6? Okay. So, first of all, we have to count the bonds here. There are 6 C to Cl bonds. 1, 2, 3, 4, 5, 6. Okay? There is one C to C bond here. Okay? I'm going to start with the C to C bond here. The electronegativity of C is 2.5. The electronegativity of C is 2.5. The electronegativity difference is equal to 0, which means this is a non-polar covalent bond, because the electronegativity difference is 0. Oh, I should have drawn this lower or whatever. Okay. Carbon and chlorine here. Chlorine has an electronegativity of 3.0. I'll write it up here. Carbon has an electronegativity of 2.5. So when we do the electronegativity difference here, and that color doesn't even show up, so let's use orange again. The electronegativity difference is 0.5. 0.5 is between 0.3 and 1.7. So that must mean this is a polar covalent bond. Polar. Yeah, definitely polar. Okay. Which means our chlorine would be partial negative here, because it has the higher electronegativity. The carbon would be partial positive. And we would draw our dipole arrow towards the chlorine like this, meaning the chlorine has more electrons. Has more electron density than the carbon. Okay, you guys are champions, and I hear third period is at the door making a lot of noise while I'm trying to make this video. Okay. You guys are champions. The legend is out.